Cool. So, hi everyone. Today I'll be presenting this action matching paper, which is quite new. And so I think I saw this paper and I find it to be quite interesting. But yeah, it's indeed very new. So if anyone has any questions or comments, feel free to also raise them, as also this paper is in submission at the moment. So any comments are welcome. And yeah, I just find it really interesting to share this paper. So let's begin. And yeah, it won't be very long. So basically, the setup of this paper is that they want to reconstruct stochastic dynamics from samples. It's similar to like diffusion models, but not the same. And so here they assume that you have access to marginal samples at different times, but the samples are not paired in a trajectory. So you don't know which samples are in each trajectory. So you don't observe the full like each one of them like as a time series or something. So yeah, the data format I think will be just like basically paired data with time, and you observe these marginal samples, and the marginal distributions we assume it to be QT. And so in comparison to like say diffusion models, well, this is maybe my summary of the comparison. So I think what's different mainly is that so in diffusion models, we're really mostly concerned with the endpoints Q0 and QT. Like we don't care about what we use a fixed sort of linear SD for a process because it's simple to simulate, and we have access to the true translational density. But it's we know that for a process and we fix it, and we don't really care about it, I think. And even the noise distribution, we maybe don't even care about it. So we only care about one distribution here, which is quite different from, say, we want to learn all of the distributions and a trajectory that basically can sample this dynamics. And it's also different from, say, modeling time series because in this time series, you observe for each, say, episode or something, you observe the entire trajectory. But here you get marginal samples. And so the authors propose some, so just to again lay the groundwork for like understanding, they propose some applications in like generative modeling in particular, where they say basically now you can relax the forward process to pretty much things that you can customize, and they consider like say for instance the diffusion, which is a sampling process that's standard. But you can also do something like super resolution, where they've done in a way where basically you actually, I think for each patch you appended maybe some noise. So say you do like 2x resolution. I think you just for each pixel you put 3 noise pixels next to it or something. But yeah, so basically it's possible to use other sampling processes other than the general diffusion. I mean, I think it's also possible in a diffusion framework to do something similar to this, but let's go with these for now. So I think they made a comparison between the standard, say, score matching, which is indeed you just learn the score for each marginal and you try to move between these marginals. Whereas here you can say for colorization, you start from the black and white image, and you just move it to like a colorized image. So that's the setting they mainly focused on. And they also focused on something like you can learn unknown dynamics from samples. And I think they like this like suggested by a reviewer, and they just added this experiment which I think is more more interesting, to be honest, because the generative modeling is too big area. I think it's more difficult to get good results. But I think they should have maybe focus more on the it's kind of more like natural science or like trajectory reconstruction task, because it seems more like interesting, and also the theory is quite interesting. So let's go to the theory for now. So basically, what they're assuming is that we'll be modeling the dynamics of the samples using like ODEs, like this in the first line, and they assume well, for the generative modeling task, so xt0, so it's the starting point, will be the data distribution, and they assume that basically V is a vector field that is basically changing also in time, and that's basically a vector field on RD. And given this OD, we have the continuity equation, which basically describes the evolution of the distribution in time given this OD, and it's given as follows: basically the partial time derivative is equal to the negative of the divergence of QT times the vector field VT. And there's also a very similar and related formula that's seen more often, I think, in diffusion models, which is the probability flow OD. And so it's given here, like I'm just including this as a reference. Here, just you get the full, like this is total derivative because x here depends on t. So that's something to be careful about. And here it's basically the total derivative of the log q xt, which is equal to again the negative divergence of vt. So very related and similar formulas. And so I was planning to do this on the by writing, but then I probably isn't a good idea. So here are some screenshots from some definitions. So the first one is just to recap the Wasserstein distance between, say, measures mu1, mu2 is defined basically for you define any for mu1, mu2, define any coupling between them, which is this mu, and you want to minimize the basically the transported distance here, and then like the minimum of this is the Wasserstein, well, it's the Pth power of the Wasserstein distance. And yeah, so obviously here you should assume mu and mu2 have like the finite Pth moment, or the samples have the finite Pth like LP norm. And so the second definition is like absolute continuity. So basically, we consider any curve in a like a metric space X, where the curve is basically a function from a time 0 to 1 to the metric space. And then it's said to be absolutely continuous if there's a function g that's like integrable under 1, such that basically so d is basically the distance on this metric space. So basically, you assume here that the distance between like this curve at t0 and t1 is less than or equal to the integral of this function g between t0 and t1. So this is the definition of absolutely continuous. And so here, basically, later they should like cited a theorem that basically is concerned about curves, but like the curves, like the elements of each curve would be a measure, and this distance will be this Wasserstein distance. And so here you're just assuming that basically this curve will be actually the evolution of the distributions, and you're assuming that these distributions are absolutely continuous in this in terms of this definition. And so basically in terms of this Weierstrass distance, basically. And that's why we are introducing this absolute continuity. And a very related definition is the metric derivative. So again, considering any curve in any metric space, we define basically the metric derivative of this curve by basically the increment of basically the distance of basically this curve evaluated at time t plus h versus at time t divided by h. And so this gives you like how far like instantaneously the curve traveled at time t. And so these basically the absolute continuity and metric derivative are very related, because if it's absolutely continuous, then the metric derivative is well defined for like t, I think, almost everywhere. And also, if you have a metric derivative, then it's automatically, I think, absolutely continuous. So, so again, these will be considered like a kind of a distributional way. So now back to like the paper. What they're proposing to do is basically like, say we are concerned about, say, learning this vector field V that can be used to basically solve these samples using this ODE, and then this dynamics of samples will give this evolution of the distributions given by the continuity equation. And so what kind of vector field will we want to learn, and what kind of dynamics can be modeled? And so these authors cited a theorem that basically says under the absolute continuity assumptions, any basically continuous like dynamics, as in the absolute continuity definition, can be modeled, and that the gradient field, like the vector field we learn, basically this V we need to learn, is basically the gradient field of a unique scalar function S, and that gives one of the solutions to like the vector fields that solves the continuity equation. And so as a result, basically, after if like the data distributions evolve as this, and then we can use this ODE to basically use this ODE to generate samples. And so just to go back to stating this theorem, basically considering like a continuous dynamic of the this like distribution QT, then there exists a unique up to like additive constant function, and they name it action S, which is not to be confused with the score because this is a scalar function. So this action function is can define the vector field V star as basically the grad of ST star, and that basically defines a QT that solves the continuity equation given here. So basically, for any set of QT, you can have this vector field, and this vector field you learned can be plugged into move samples such that the marginals are QT. So this is like the generality of the proposed approach. And then it'll be constructed later. So for now, basically, this is like first saying that this approach is general enough for suitable applications, and secondly, it's basically saying that in score matching, right, we learn vector fields as just like vector fields, but here they have constrained the class of vector fields they learn to be the grad of some scalar function. which has appeared before. I'll get to it a bit later about a little bit about this.
Yeah. I think you have a confirmation. In terms of the lecture which you did like you can either like choose a domain.
Yeah.
Like you could also like find a lecture which will get into it.
Yeah.
Why so I don't understand how is it doing this.
So I think yeah.
I think the issue is being constructed there as like non-trivial. So if you take a gas station, that non-trivial curl, so it's not a great.
Yeah, it's not a it's like curl, like it's not a gradient field there. Like you can't like I think the thing like the gradient field. I think like you have a gradient field. You need to think like well have a scalar like they say it's also I think very related to like energy based model, right? So you have a scalar that you need to basically define the grad such that it's rotating is theoretically not possible.
So it's not the unique B, but it's the unique right?
Yeah, so it's the unique. It's unique S. Yeah. And so this S also has some nice properties and also very related to the optimal transport. The first thing is that this solution VT star equals to the grad of ST star minimizes the kinetic energy, which is defined here to be the integral in time of basically the norm of the squared norm of VT and like taking expectation with respect to QT, so with respect to the true data distribution at time t among all of VT. So basically, this grad of ST star is the minimizer of this kinetic energy. So among all of VTs such that the continuity equation is solved. I should clarify. Yeah. So basically, one can maybe already see here that like seems that this optimal VT star is moving the least from say distribution to distribution. And so to maybe formalize that into more like optimal transport, then basically this grad of ST star is the limit of, so at time t, like to again clarify, is the limit of the OT map between two very close distributions on the curve. So like say you consider T star, which is actually the optimal transport map of the like using the defined in the like a Wasserstein 2 distance, and you find the OT map that solves it. And these like this T star will be basically dependent on these two distributions. Is the solution of these two distributions, the coupling of these two distributions, basically. And so that if that infinitely close, then we expect that it won't move too much. And so like minus this function like with the identity and take the basically divided by dt, you get pretty much the this vector field. So this is the connection to OT in one way. And also it gives you a little bit of the something to say about the Wasserstein distance itself as well. So basically, if you were to say what's the increment of the Wasserstein 2 distance between qt and qt plus dt, then it's also just equal to basically the kind of related to the kinetic energy at only at time qt at time t. So basically, you can say maybe already a lot given this optimal solution grad of ST star. And as an aside, I think these theory are also very related to the more like general optimal transport and gradient flow sort of theories. And so, for example, I say like as an aside, this is not on the paper, but very related is like, say we want to compute the Wasserstein two distance between two measures mu0 and mu1, then actually this is one way to like calculate this Wasserstein two distance is that it's the minimum of again this kind of kinetic energy among all vector fields that solves this continuity equation and among all intermediate distribution. So here again, we're not very relaxing. Like we're not saying like as an aside, we're not saying the mu t from 0 to 1 is fixed in any way. But this when we also like take the minimum across all of these measures, then you actually recover the basically optimal transport plan, optimal transport distance. Yeah. And the other like also very related, I think, characteristic of this optimal transport plan is that for like say an OT map between mu0 and mu1, then if you define also like if you define mu t to be the push forward of this mu0, where t is basically the linear interpolation between the like the after transport and the before transport. Then actually, so already given this, this gives you a basically a constant speed geodesic in respect to the Wasserstein two distance between mu0 and mu1. So actually, so basically this means that this mu t is, I think, just the solution in this minimization. I'm not an expert, so correct me if I'm wrong. But yeah. Anyway, so as an aside, I think the like this paper doesn't mention these, but they're quite interesting and very related. So now to like how to learn the action, the authors propose something called action matching, which basically the high level idea is that we, again, like score matching, we want to learn an action, ST. So the ST will be the variational action to minimize this action gap that's integrated in time and also like weighted according to QT. So we want this variational action to be like such that the grad is close to the true gradient field. However, this is not tractable definitely because this true action is not known. So we want to learn ST to approximate it. And so instead, the paper derives a lower bound on not on the action gap, but on the true kinetic energy. So that's basically like we have discussed before. This is the kinetic energy, but here is like the true action, and they derive a tractable lower bound on this energy, and they want to basically, I think, maximize this lower bound. And so they define this kinetic energy lower bound as basically 4 terms. The first term, like the first 2 terms, is sort of interesting because you get the increment of the action between time t1 and t0. And so this term can be seen as we want to basically maximize the action maybe at time t1 so that the samples will move to qt1 at time t1. So if as t1 is high in areas where qt1 is very the densely distributed, right? Then st1 should be high because then like gradient field will point there, so that like the samples will move there. And maybe I think this one is more like, well, I think these should be viewed like together in context, say, talk about different terms, like what their meaning is. But if you really want meaning on this, maybe it's saying, well, we want the samples to move away from qt0 towards the areas of qt1 and also the intermediate distribution. So that's maybe one way to think about these terms. And then there are two other terms where the authors say these are smoothness or regularization, but I'm not entirely sure about this last term. And this third term is seems like indeed a regularization, which basically tries to minimize the learned kinetic energy. So this is actually like lower bound on the true kinetic energy that we want to maximize, but here actually we also have a regularization that actually so we kind of are maximizing this kinetic energy lower bound on the true kinetic energy, but we're also kind of minimizing kinetic energy of the learned gradient field, which is somewhat interesting. So this is definitely like a regularization term. And the fourth term is like a time derivative of st of this action function. And they seem to say, well, this is a regularization term because when we maximize this, we also want to minimize the time like derivative of st. And so they're saying it makes st smoother in time, but I mean it's not the absolute value, right? So I think this is different meaning. So I don't know what I have I'll get to it later maybe. So, but after we define these four terms, and they show that basically the true kinetic energy here on this page is equal to this lower bound plus the action gap. And so because we want, and this true kinetic energy is a constant that we don't know. And because the action gap is greater than 0, we have a lower bound to this true kinetic energy. And at the same time, because this is fixed, we can just do basically maximization on this lower bound in order to minimize the action gap. And so this is the learning algorithm they proposed. And that's basically if the action gap is 0, then this k elbow gap is basically k elbow equals to the true kinetic energy. And so, like I said, these first two terms maximizes the action increment. The third term it minimizes the kinetic energy in regularization way. But the fourth term, I feel like it's sort of if you want to make it make the time derivative to be you want to minimize it. It seems to me that you're trying to decrease st in t along the path. Because I don't really know what it means, but also I don't think you can view all of them like each term individually. So actually, if like for instance the true qtx is like fixed for a period in between t1 and t0, and so basically like if qtx is not changing, then I think you can basically move this expectation outside because it's not because this is not dependent on t. And so this integration will now be just again kind of similar actually to these two terms. Will give you another action increment, it seems. And so if we have another two time, like say t2 and t3, so if it's like t0, t2, t3, t1, then I think it should give you something like action increment between t1 and t3 plus action increments of t2 and t0, something like that. But I'm not too sure. about this, but I don't think it's regularization, as they say. Not for sure, but I may be wrong. Anyway, so this is the proof of this K-elbow lower bound. It's not very interesting, and also they assume here that there's some weighting function on the action gap, which is not introduced in your main paper. So this is making it more difficult to read. So basically, if you want to read it, you can ignore all of the weights, and that recovers the original definition. But mostly speaking, it uses two things. So all of these are, algebraic, just, expanding out this square norm, and then you cover, like, at the last term, the true kinetic energy. These are all just the simple algebraic changes. And so the first thing they use is kind of like a divergence theorem, and like the divergence of basically they modified from this to this using a divergence theorem, and then they used here like a integration by parts, in time, and that gave the basically the I think the time derivative in S, and also the action increment in the first two terms. Yeah. So if you want to have a look, so all of these are very straightforward. These are the other terms are also straightforward. It's just this one and two. They use the two things. So it generally seems like a very neat approach, and the proof seems to be also neat. And so as a result, so I think it's just very neat result, very interesting. But I'm not entirely sure if anyone else has thought about it before. But this is definitely very interesting to me, a very neat contribution. And so in terms of practical implementations, so this is indeed different from score-based standard SVMs, because we will learn the vector field on RD directly in like SVMs. And usually for images, we have like units, and basically like the output dimension is exactly the same as the input dimension. But here we don't do, like in this paper, they don't do that. Instead, they use the vector field using the gradient of a scalar function. And this is very much related to like energy-based models, because in energy-based modeling, you essentially have also a scalar function that gives you the sort of the unnormalized density of the distribution. So this is essentially basically very related to energy-based modeling. But energy-based modeling didn't achieve like the same kind of influence as diffusion models. And so as a result, one of the explanations of this is basically how do you parameterize ST? How do you parameterize the ST function, which is a scalar function? And so if you were to like say use some kind of classification or something, maybe it won't work as well, like because you would like at the end you do a lot of, instead of like a UNet, at the end you have a lot of like traditionally we think of a scalar function. We would use something like average pooling and something blah blah blah, and at the end it gives you a scalar. So like it shrinks the image, and then up to a point where it's a scalar. But perhaps I think this paper, I think experimented with the different parameterizations of ST, and I think they decided to use instead also a UNet model, but defining it like the ST in terms of UNet. So still we want to maybe have some kind of UNet here, but instead of using a UNet, as a vector field, what I've done is that they plug it into a norm where basically the ST of X is now like the norm of X minus the output of the unit. And so if you take the gradient of ST, then get this. And basically the first term is very related to score-based generated models, because this is essentially like sort of the noise you're predicting, right? So like say FXT is your prediction of your of the data sample given X set times 0, and X is like the noise version of the data, and F theta X is your prediction of the true data. Then this is like noise that you learn in the SGMs. It's like the epsilon parameters like something. And the second term here, I think, is what, so this different thing is what guarantees it to be a conservative vector field. So basically, you like if you just model any vector field without any restrictions, then you don't have the property that there are all gradients of some scalar function, kind of like what we were discussing earlier. But so is this restriction a limitation of energy-based models, or is it not really? It's maybe a question. But I think so. In this paper, what I'm doing is still, I think, in like the diffusion context, they parameterize the vector field. I think using this basically the gradient of a scalar function. And as a result, you get a very much reduced set of vector fields that you could directly learn. But I think the result they got is like on par with the standard diffusion models. So they argue that basically the energy-based modeling area and score-based generative modeling area should probably better reconcile the differences, because like one could argue that it's this improvement, like enlargement of the vector field V that helped like score-based generative models to achieve great performances. But actually, maybe it's not just in the enlargement of this set, but maybe it has to do with the parameterizations of ST, because previously maybe for scalar functions we don't use like something like UNet, where we're just the definition of the neural networks are not as well investigated, and so the results have been worse. And so they say maybe so learning of ST as opposed to like VT is still like a feasible and not worse approach compared to SGMs. Yeah. So this kind of parameterization is what the authors of this paper, the action matching paper, also adopted for learning ST. So yeah. And so like now I go through the like argued benefits of their proposed approach. The first one is that it only relies on samples at each QT, so marginal samples. And so it enables more applications such as trajectory reconstruction. So if you don't observe any trajectories, maybe you can infer some trajectory. If the underlying trajectory is generated using the ODE, I think. Right? But if you don't have this, if you don't know anything about the underlying trajectory, then maybe you can't reconstruct it. But here you do have a way to move in between these distributions using LOD, but not necessarily true like trajectory, because it might be like noisier version of if it's not generated by LOD. And also, like as I said before, they have some custom forward process, like as opposed to like noising process, they have processes that's like from color to uncolored images, things like that. And so this enables more applications. And the second thing is that because of the optimal transport theories, the learned ODE may be potentially easier to solve. Because of the theory I've covered, and also maybe because the vector field has some properties, things like this. The third thing is that in some cases, I think you won't need to learn a complex score. This is like a plot that the authors provided. Basically, if you want to like have this kind of dynamics from time 0 to time 1, then the true like dynamics for each sample is very simple. But basically, you just want the vector field to be like just constantly moving to the right, and that's it. So you don't need to learn anything complex. But given this like dynamics, if you want to instead use score matching to like for each marginal, you want to learn the score for each marginal, and then use like score like you do like SGLD or something on the for each marginal at each time, then like you need to learn more complicated score basically. Here, like in this case, you don't like using their approach, you only need to learn a constant vector field. And so they've shown some like I think the results like experiments are mainly there, maybe something that they could improve. Basically, they show that for like generative modeling, they focuses more on like these conditional tasks. But basically, the result you get is not as good as score matching. But they have like they describe that the reason is probably indeed because you don't actually have like trajectories. You only observe samples. You don't know any score. You don't basically you don't learn a score using denoising score matching, and you don't know that each what samples are from the same trajectory, things like that. So actually, the like performance is not as good as score matching. But they say that basically, if you do, if you use the kind of just like say for colorization, if you use something like like data, so colorized image to not colorized image, and vice versa, and then you convert fast, and the score matching, where the score matching starts from noise, basically. And another application is like they basically want to simulate some basically dynamics, say like this one, and they compare their approach with like score matching, and they basically use some Langevin dynamics to sample at each basically I think marginal distribution at each time. You instead use like some Langevin to simulate the distribution, so simulate QT using the learned scores of QT. Then probably it's worse indeed than this approach because learning scores might be difficult, but learning the dynamics might be simpler. And so they achieve a more precise simulation of the true dynamics, so showing this ring curve. So this is the experiment where they showed the benefits of their proposal. Yeah, that's it. That's the end of my presentation. So it's very
question.
Yeah.
Is that then that problem kind of the same as the multinational Schrodinger bridge? Because with the Schrodinger bridge, you that you also try to minimize the optimal transport distance with some kind of variability.
Yeah.
Whereas in that case, the regularization is exactly zero. Because in the infinite decimal limit, you have the gradient which is exactly the limit of transport map. Whereas the multiple Schrodinger bridge, functional unit is more regulated. Quite strong with it.
Yeah, I feel like there's definitely a strong relationship with something with this approach.
Yeah, I think the application is actually related to what Dan just mentioned. There's this paper where people have been actually asked paper like tutoring on this JK net and stuff on what they're trying to do. The problem they're having is coming, I've forgotten the kind of detail, but they have this application where really they observe the marginal of stochastic process by full sample, and they're trying to fit actually some kind of like a dynamic to it. And the way they do it is it's super complicated. Actually, this approach can be much more promising. It's a paper by Tuturi on, I can send it to you.
Okay.
But they have a very nice application. There was this distributional regression, which is the kind of same problem on it's related to, it's usually formulated as multi-marginal optimal transfer. Which seems like a really interesting approach.
Yeah.
Right. Is it possible to formulate the same, but not using the scale and using it? Like, you can get it lost. So you don't feel.
Yeah.
But I just feel like people in school, like, oh, be conservative, like that, conservative, like that. But I don't really like to do that.
It's not that useful, yeah.
Yeah, so I'm just wondering here, if like, is it being conservative or being the same?
So here it's not possible.
Yeah, like here the scale of our life, you can start again. But I don't know if that maybe the
I don't know. I mean, well, I feel like it's very much maybe reliant on the fact that yeah. So I think even at this step, they swapped from the grad of ST to ST. So if there is an approach to do it using vector fields directly, then you can't be doing this on this step. Then it seems to still involve. Yeah, the thing is like this is what they this is the like the continuity equation. So they swapped this term in here, right? And so it seems that these are. I don't know if there's a possibility, but yeah, I think their proposed approach is very much reliant on the fact that S is a scalar. Yeah, yeah, but it's perhaps also more complicated in the like in practice because of these time and the score derivatives. But at the same time, yeah, I find this is indeed very different from like you say score matching because you get this term. It's like not like also this action increment or and also this time derivative is just not like nowhere to be found in like score matching.
Is there any other possibilities for that that we are aware of?
You mean like choice of assets in like the
implementation, the specific form?
so they definitely choose they chose this form for all their experiments. So S will be like so I think here what happens there's also a detail I think it's like if S is like this, right? Then it's actually but like if like you want to do something with ST here, it's actually I think a bit difficult because you want to like say you want to if you want to maximize this first term here, right, at time t1, then actually it doesn't make a lot of sense here because if there's a minus sign here, then you will be minimizing this distance, which makes a lot of sense, right? So it's like you're predicting, you're doing a regression, like you're predicting what's the like. I'm not entirely sure actually. Yeah, so this is a choice of, it's actually a bit interesting what this is. Yeah. Oh, sorry, it's not like regression. That's wrong, sorry. So basically it's like, well, you define a center and it's not regression. So it's like, say you have a Gaussian thing, right? Where like this is the mean and you want, like this is, so this is the mode that you want X to be in, I think, something like that. But yeah, maximizing this just seems very weird to me. But in their application, T0 is the data distribution. So actually there's a minus sign. So they're actually minimizing this term.
Any other question? Thank you.
Thank you.
You can stop recording.